Ready whenever.
Okay, so thank you for, are you recording? Yes, it's recorded. So thank you everybody for attending this section on the Cruz. The topic is for open source hardware. And we have three nice talks. The first one by Mark, working on Google and let's talk about XLS. Then we are gonna have a talk by Tim Sherwood from Santa Barbara. And he has been working in a lot of projects like PyRTL and things like that, many things. So been a faculty in Santa Barbara. And then we're going to have a panel. So the way I put it is that we have the two talks at the beginning. One of the panelists is teaching a class now, so she couldn't come. So we moved the panelist, the panel a little bit later. So the idea is that he will join. And the idea of the panel is to talk about different IRs for hardware. So it's a little more narrow focus, not only on open source hardware, it's more IRs, what are our experience, what did we like, what didn't like. And there are sort of questions, and Sheng is going to be the chair of that panel. So he will be policing everybody. So I talk too much, he should kick me out too. And then the idea is that the panel has around 1 hour, but if there is enough time, and I think it should be, then we have the talk by LifeSD, the two peers, Sheng and Sakshi. They will give a 20-minute talk combined, and it's the work we are doing here in UC Santa Cruz. So with that, the first speaker is going to be Mark Heffernan. So he's a software engineer at Google, and he's been working in XLS. It's a very nice project. I've been following quite a bit at Google. And he has experience with several things, GCC, LLVM. He's working on XLA. Before it's a different project that I have. And he received the PhD from UC Davis. So you went ahead, you can share the screen.
Yeah, thank you, Jose. Let me get started here. Let me share my screen
One quick thing while you start, do you want, if we have questions, do you want in the middle or do you want to wait more to the end? So you're mute.
Okay, can you hear me now?
Yes.
Okay, yeah, so why don't we, if we can't keep the questions till the end, it's a pretty quick talk.
Okay.
And then we go from that. Okay, so let me, sharing killed my mic, so hopefully this won't, there we go. All right, can you still hear me? Great.
Yeah.
Okay.
Yes,
all right, here we go. Thanks, Jose, for inviting me to give a talk here. My name is Mark Heffernan. I'm a software engineer here at Google. Been here quite some time, doing a lot of work in various compiler projects. And I'll be talking today about a project we're working on called XLS, which is an open source HLS compiler. My teammate Chris Leary gave a talk, kind of overview of the XLS project at this forum last year. I'll be kind of give you a very brief overview of XLS and then kind of dive into the details. Specifically, I'll be talking about the IR, kind of motivated, by our later discussion here. And so first off, what is XLS? It says it's an open source HLS tool we're developing here at Google. As everyone here knows, it's kind of the end of Moore's law, and there's, we're entering the age of accelerators where there's increasing demand for compute, but they can't be satisfied by the next CPU generation. So lots of specialization going on, and what we're trying to do is make that process easier, enabling hardware design at a higher level, improving the increasing hardware engineer productivity, as well as enabling SiFive to also contribute to hardware development. Of course, that's something that could be very valuable to Google because we have zillions of SiFives, and if we can leverage some of that to help out with accelerator design, that would be a big win. And so the team, XLS team, we previously worked on a number of other open source compilers. We had a CUDA compiler, then also XLA, which is a compiler targeting machine learning space. and accelerated linear algebra. It's the compiler used for Google's TPU machine learning platform, as well as targeting GPUs and CPUs. And I think with our past experience, we've kind of shown that we can kind of demonstrate, success with a fairly small team, developing a kind of focused tool chain, addressing some, specific need. We don't need an enormous team. We're not going to try to solve all the world's problems, but if we can carve out some set of interesting, impactful problems which can be addressed with a tool chain, in this case, HLS, we hope to have success. And we hope to do the same here with XLS. And it's available on GitHub with the link you see there. So this is kind of all the different parts of XLS. I won't talk about all of them, but maybe just a few highlights. We have a domain-specific language, a custom domain-specific language we have called DSLX, as well as a C++ front end. We have, which then gets converted into an IR, and then our intermediate representation, which will be the focus of this talk. We have a core compiler, which kind of does optimizations, and also a scheduler for generating pipelines. And then that code generator, which generates Verilog for synthesis or simulation, as well as a lot of other auxiliary functionality to support kind of the main HLS flow. We have like a fast functional simulation via LLVM JIT, formal verification, fuzzer, visualizer, a number of other things. Again, I'm not going to talk about all those other boxes. I'm going to focus here on the intermediate representation that we use in XLS. What is it? Why did we design it that way? And maybe highlight a couple of details about it. So for those of you who are not compiler people, maybe a quick overview of what a compiler IR, an intermediate representation, is. Basically, it's a data structure inside the compiler, which captures and represents the semantics of the source code of the source program going in. It's designed to be easy to manipulate and analyze. One way of thinking about things is source codes or source programming languages are designed to be human readable, human writable, while intermediate representations are more machine focused, easy for a machine to manipulate, transform, and analyze. And typically, a IR includes a fixed set of operations, like primitive operations like add, subtract, logical operations, things like that, branches, with very precisely defined semantics. And the way the compiler works is it takes its source code, lowers it into this intermediate representation, and then just iteratively churns on the IR, analyzing it, transforming it, optimizing it, and gradually lowering the abstraction level until it, at the end it emits, some low-level target. In a traditional compiler, that's assembly language, and an HLS tool like ours, that might be Verilog, while like an EDA tool chain, that might be a netlist. And so just to kind of contrast, the XLS IR from, and maybe motivate our design, I'll talk a little bit about what a traditional compiler IR looks like. This is something you might see in GCC or LLVM, and it looks very similar to assembly language. You have this ordered sequence of operations. They're taking data from registers typically, and writing data out to registers, and with some memory instructions and control flow with branches. And so you have a control flow graph on the example bit of IR on the right. This is from LLVM for a particular example function. You can see some pretty primitive assembly type kind of assembly plus kind of operations, comparison, branches, multiply, loads and stores. And this particular function is broken into like 4 basic blocks. And why is a traditional compiler IR kind of built that way? Well, the target for a traditional compiler IR is kind of reflected in the machine language which it targets, is the underlying compute substrate is what's called the von Neumann architecture. And there are a couple of kind of key attributes of this architecture. One, you have this kind of big shared memory, global memory. and control unit, which then takes a sequence of instructions and executes them essentially one by one, and that, which is then used to control the registers, control the functions, control data flowing from memory registers to function units and back out to memory. And the key properties here is that it's sequential and that it has global memory, and that kind of informs the design of both the instruction set as well as the traditional compiler IR. But XLS is not a traditional compiler. What we are doing is targeting hardware, and hardware is a widely different beast than as a target than your typical CPU. Specifically, hardware is data flow, where data dependencies are all explicit. They are wires in your hardware. Everything is concurrent. So I mentioned before that the properties of this von Neumann architecture is this sequential execution. And in hardware, everything is concurrent. The little circuit there on the right is a simple little circuit which I think multiplies two 4-bit numbers. And you see those AND gates in there. Those AND gates are all executing concurrently. They're not ordered relative to the other AND gates in any sense. Everything is happening all at once. All interactions are local. The AND gates are wired to particular inputs and wired to a particular output, and those are the only things it affects. There's no like global memory, big bag of state on the side that it can reach into and manipulate. And also, accordingly, there's kind of no precise analog to your normal program control flow of branches, of basic blocks, things like that. It's a very, very different compute substrate, if you want to think about it that way, than your traditional compiler. And because of that, we designed the XLS IR as a data flow IR. And what it looks like is it's a directed acyclic graph of nodes, where nodes are operations, these primitive operations, somewhat similar to what you might see in a traditional compiler IR of adds and subtracts and logical operations and some hardware specific things like slicing out bits and things like that that come up often in the hardware world. All data dependencies or edges, nodes in the graph are operations, edges in the graph are data dependencies, and all the data dependencies are explicitly represented. There's no implicit dependencies through some aliasing in memory or anything like that. It's all very explicit. And there's no node order. There's some partial order defined by the edges, but of the graph, but no sequential order that you might have. And this is sometimes called in the compiler world a sea of nodes representation or graph-based representation, IR. And again, the motivation here for having an IR like this is that it really reduces the impedance mismatch between your program representation in the IR and then the kind of target, the hardware target. We can kind of very directly represent exactly what we want to emit. And that has a lot of value. And here's a little bit of an example here of where we have our domain-specific language, DSLX, on the left, and the corresponding XLS IR in graphical form on the right. DSLX I won't talk much about it. You can see Chris Leary's talk from last year. He talked a bit more about it, and its syntax is kind of inspired by Rust. So if you do program in Rust, it should be pretty look at least superficially familiar. In this case, we have a simple function which takes an opcode and two data values, and then based on that opcode, performs some operation on it, and then returns the result. And this is done via this match statement. And then the IR, which is generated from this simple little program, is you can see the graph on the right there. The left side of that graph, you see X and Y, the data inputs, fanning out to these various operations, the add, the subtract, and the OR. And the right side kind of has the control flow, or the control side of of this particular example, where it takes the opcode, compares it to various values, and then based on those comparisons, selects one of these operations. So we also have a textual form of the IR. Every line in this this text here corresponds to an operation, a node in the graph that you saw before, and it's typed. It has a little bit more information than you would see in the graphical form. And so that's kind of superficially what it looks like. It's a data flow IR. We have in the IR, we have 3 different high-level constructs. We have functions, which is the example I showed before, which is a stateless computation, some number of inputs, some computation, some output. We have procs, which is our method of implementing state. And then we have blocks, which are kind of a lower level, RTL level representation, which are used for code generation. In the next couple slides, I'll talk a bit more about procs and blocks. The IR itself is statically typed and statically sized. We support bit vectors. Again, of a fixed size, compile time known size, 32 bits, 64 bits, 17 bits, whatever. Tuples and arrays, again, all statically sized. You can have compound types. You can have tuples of arrays of tuples, and so forth. We also have these things called tokens, which are used for ordering particular side effect operations. I won't talk in too much detail about that. Values in the IR are all immutable. And that kind of simplifies the analysis and representation. You don't have, right after read hazards and things like that. Everything is kind of implicitly SSA because of that single static assignment. We have about 60 different opcodes, familiar ones, add, subtract, logical operations, as well as some special purpose ones for representing RTL level constructs or procs, etc. So first thing, kind of maybe interesting bit about the IR I'll focus on, which is procs. And this procs, as I mentioned before, are the way we represent state. So functions, we call, are totally stateless. You have an input, it produces an output. Procs are the mechanism within XLS of representing state. They're inspired by communicating sequential processes, where you have these objects which have some state and communicate to other similar objects via channels, which are essentially infinite depth FIFOs, abstractly. And so these procs, these communicating sequential processes, they kind of operate independently, but just communicating to others by reading and writing data values, flow control data values to other procs in the design. So simply, a proc is a pretty simple construct. All it does is it reads its data, which has blocking reads, computes something on it, and then optionally writes out a value, updates its state, and repeats. And that's all it does ad infinitum. And then with this network of these things, it's quite expressive. Can represent kind of arbitrary computation. The example on the right is a simple example which computes a sum of products. It takes a pair of values through those 2 channels on top via the receive node. It multiplies them together, adds them with whatever its current state is, and then sends that value out of the proc through the output channel at the bottom. And then it updates its state with that value it just sent out, and then repeats, forever. And so this is essentially adding, a sum of products. It takes pairs of numbers and returns the sum so far of a sum of the products. And many tasks kind of naturally map onto these procs or networks of procs. For example, encoding and decoding, compression, encryption, decryption, signal processing, applications, can all be represented with these little boxes of, little black boxes, which do some little bit of computation and send results along. And with procs, it's easy to construct latency insensitive designs, specifically process networks, which are these networks of these procs with particular constraints on on their operations, and being latency sensitive is a huge win. Basically, that means if any functional level simulation of the design will match the cycle accurate simulation. So you can potentially vet the design a lot deeper at the functional level without having to rely so much on the cycle accurate simulation, the much lower cycle accurate simulation. And procs and these networks of procs are kind of the way within XLS that you define the architecture. So there's a spectrum of abstraction in the HDL, the hardware design world, maybe starting at RTL and going all the way up to the highest level of going up to generators and then up into HLS space and kind of the highest level of HLS space. The highest level might be you have some C++ nested loops, and then the compiler chews on that. It generates your RTL with some memory co-optimized with your RTL through some very deep compiler magic. We're targeting a bit below that, where we get more of the architectural hints and design from the actual programmer or designer, rather than potentially the highest level. We hope it's kind of a sweet spot for giving control to the designer or programmer, and that they're kind of designing the architecture, but helping out with kind of the nitty-gritty bits of pipeline, of managing timing and pipelining and things like that. And so a simple example proc there, network on the right is the JPEG decoder, where you have some compressed bit stream coming in. It does Huffman decoding and delta decoding and run length decoding, dequantization, and then fans out to maybe multiple procs. Each one of these boxes here is a proc. Doing inverse discrete cosine transform, merge the results together, and color, do some color conversion, and out pops an RGB bit stream. And so in this case, and then here some of the procs are stateful. The Huffman, the delta decoding at least are stateful. And in this case, as it has been coded up by the designer, has kind of designed the architecture here. So we might have multiple units doing IDCT because maybe that's compute intensive and you want more horsepower there. Those kind of design hints are coming. Architectural hints are coming from the designer, and then XLS kind of takes care of the details. Another thing we have in XLS is blocks. These are kind of a lower level RTL corresponding to RTL level, and have things like clocks and registers, ports and instantiations, and kind of roughly correspond to a Verilog module. All functions, everything that gets lowered into Verilog goes through these procs, goes through blocks, and it enables kind of a very precise correspondence between what we have in our IR and what we generate in Verilog. Running a little short on time, so I may skip the details of this slide. But general, like any compiler, we have a set of analyses and passes. And one thing I will note is that the data flow IR often makes many of these passes and analyses much easier, because you're not having to deal with control flow and reasoning about control flow. You can just concentrate on the data flow side of things, which makes some passes just tens of lines of code. It can really simplify things. The project status, we've been at it for about 2.5 years. We've taped out a pretty complex multi-cycle feed-forward pipeline, and more design wins are in progress. Our current focus is making procs more expressive, more powerful, in order to build up larger, more complicated design. Previously, we've been kind of focused on feed-forward stateless computation pipelines, and never-ending optimization work to improve QOR. And then we hope to also tie into some open source ASIC flows. We've mostly been focusing on the ASIC side, because that's what is more interest internally at the moment, and hope to tie into some ASIC flows. We have a bunch of internal contributors, some on our team, some outside our team, as well as some contributors in the open source world. I think that's all I have. Kind of a whirlwind tour of XLS and its intermediate representation. Reach out if you're interested in contributing. There's a few links there to mailing list and source code documentation and last year's talk in this forum about XLS. Thank you.
Yeah, very nice talk. There is any question? So we have you can ask directly, so you can unmute and ask. No questions. Okay, so I have some question.
Oh, there is a questions on
There's
chat.
one question popped up there.
Okay.
Says, do we have plans on moving to MLIR? That's a good question. We're at Google certainly MLIR is on our radar. Early on, I should say just generally, adopting external dependency on a framework has some immediate benefits potentially of like you don't have to implement what they've implemented, but also there's some potential downsides if you're not like perfectly co-aligned with whatever invariants or constraints that they may be or goals that they may have. I think when we were kind of working on XLS at the beginning, we didn't know really where we were going, so there was a lot of uncertainty on our side, and so we opted to build our own IR infrastructure for those reasons, because if you tie yourself into some other framework and you want to do something a bit different, it can be very hard if that's not co-aligned with whatever the other framework is. So we opted to do that ourselves, and so yeah, so we'll probably continue to do that. It gives us maximum flexibility. We may have to write some a bit more code on our side. That's not to say we're totally against reuse. We use LLVM as our JIT. We'd be crazy to write our own JIT. But that was much more well defined than say what our IR was going to look like with a lot of uncertainty, forward-looking uncertainty.
So I have a question. Well, I thought there was someone making a question, but when you do the annotations, do you annotate the source code location and then you propagate through the flow? And what happens is you start to do transformations. You might lose source load.
Yeah. This is
a
classic problem. Yeah, I guess you noticed that the position annotations there in compiler optimization, where you have you're losing, like in the traditional compiler flow, you have your debug information, which gets out of date as optimizations.
So how do you deal with that?
It's best effort. What we do, if we are replacing, oftentimes a typical transformation will take some expression and replace it with another expression. We will copy over the position information, so we will propagate it as best we can. Propagating also like the names, original variable names, and things like that, in hopes that we'll still have the correspondence. But there are no hard guarantees there. There may be some loss of the position information, but we do our best. This is a known kind of hard problem in the compiler space.
Is any other question?
Yeah, I had a question. Can you talk a little bit about your experiences with pipelines that have restarts or sort of feedbacks that are coming back in a single cycle with XLS? Yeah, sure. We're just kind of entering that support for those things with procs. At the previously we'd been focused mostly on feed-forward pipelines. Not a lot of experience, more forward-looking. And how we are going to handle this. This will be represented, at the input source level, like DSLX, at the IR level as well as a proc, which is one of the stateful, a stateful object, where the state is something which is recurring, from a later pipeline stage potentially to an earlier pipeline stage. And that in our world, that represents an interesting scheduling problem. It affects how you're going to schedule the pipeline, where scheduling is just kind of dividing the various ops amongst a pipeline schedule. It adds another objective of not trying to just minimize the number of stages, meet timing, as well as try to make this feedback loop as tight as possible. And so we're just kind of exploring that space right now. We'll probably, initially have something, just trivial, just only enable like short feedback loops that can be done in a cycle. Otherwise, give up with better and better support coming down the line. Does that answer your question?
Yeah, we'll look forward to what you guys find out.
Do we have any other question?
Yeah, I have a question here. So the design of Accelerator, does it account for multi-clock domain designs?
We don't deal with it at the moment. The architecture, if you have a network of these procs communicating via FIFOs, can kind of naturally map to multiple, clock domains where FIFOs, help you cross those clock domains. But we, haven't explicitly, addressed that. But I think it can naturally map to multiple clock domains, these architectures.
Okay, thank you.
I have a quick question, last one before we move to the next speaker. Is do you across the procs, do you have FIFOs, or what type of handshake do you have across them? Or do you have a back pressure? What do you have there?
Yeah, so abstractly, as far as the semantics of the procs at the source code level, they're like infinite depth FIFOs. And then that has to get lowered to something physically realizable, of course. And that may be a FIFO. It may be with sufficient analysis, you can say, hey, actually, I don't need a FIFO here at all. This can just be a wire. So a channel doesn't necessarily have to lower to a FIFO with, full ready valid flow control, in both directions. Yeah. So, with sharper analysis, you can lower it to something less expensive. But in the general case, yeah, it would be ready valid flow control FIFO. Or the equivalent, to ready valid.
So let's thank the speaker. Very nice, interesting talk. A lot of questions, but we have to move to the next one. So the next speaker is Tim Sherwood. So he's a professor at Santa Barbara or Santa Cruz. I was going to say Santa Cruz, but no, it's a beautiful picture of Santa Barbara. If you have not been on the campus, I'm sure you will enjoy. And he's going to be talking about the work he's been doing, some of the things we have been using quite a bit.
Great. Thank you. Yes, thank you for the introduction. Yes, I'm at UC Santa Barbara, and this is joint work with myself and Jonathan Balkand here. Jonathan actually brought up a point that there's another university or peer institution, Berkeley. They love the view from Berkeley, and we're like, hey, the view from Santa Barbara is pretty good too. So maybe we should start showing that off as part of our what we're trying to do in this hardware space. One of the things that I just want to start with, I think actually the last talk was was an amazing talk, and it really kind of set the stage for some of the things I wanted to chat about. First and foremost, I think that we're dealing with as was mentioned, that we're dealing with a lot of uncertainty in many different types. There's global uncertainty around hardware and the future of hardware. There's shifts in the underlying technology that, both in terms of the, just transformative change in the way that we design systems and hardware or software together. Another change is just increasing corporate verticality, that basically, there used to be a much bigger line between hardware companies and software companies, and as we're seeing, this is no longer the case. So we have to manage all of this uncertainty and complexity in what we do and prepare for that. One of the reasons that this is such an exciting thing to look at in terms of IRs for hardware and just in general new techniques for developing hardware is that they bring some really interesting and useful properties to what it means to be a computer. As was kind of pointed out in the last discussion, I don't think that abstractions for doing this well are totally understood yet. And so there's a lot of innovation that's happening. There's also the need for even more innovation, and we have to kind of figure out how we're going to lean into that. Some of the reasons that people were, wanting to bring this hardware software across this divide so much is because, you know, it brings in huge opportunities for new levels of efficiency in the computing we do. It also, but that's not the only reason. That's one reason, but there are other reasons as well, because there's sometimes properties that it's very difficult to get out of our computers, you know, such as, you know, strong notions of security, where if you bring hardware into the mix, you may be able to do that. But at the same time, it also brings properties of inefficiency and insecurity. It's very easy to, in security, it's very easy to add some new hardware and be totally confused as to what the impact of that is on your design with regards to security. It's also, as you start sort of bringing software and hardware people and crossing that line, it's very easy for people who are come with a software mindset to write things that look good as software, but are horribly inefficient hardware. And so we need to figure out, how do we close this gap? There's, you know, this gap in understanding of, like, if we're going to start working in this space that exists between hardware and software, how do we get people who are coming from the software side to understand the, you know, the efficiency ramifications of the software that they write when you turn it into hardware? And likewise, how do we get people who are traditionally thinking about hardware to start thinking more like software people and start thinking about not just how do we build new modules, but how do we build new abstractions? How do we build new ways of building into the tools and languages that we are working on? And, you know, I think it continues this point that hardware is increasingly soft, meaning that we are having more and more hardware that is configurable and, you know, really is either generated from software descriptions, or the hardware is tuned to software descriptions. At the same time, software is increasingly hard, meaning that, you know, the traditional boundaries of what it means to be a software person and what it means to be a hardware person are increasingly permeable. And that, you know, when you write software today and you care about these properties like efficiency and security, just as an examples, you have to know what the hardware is doing under there. So there's no escaping that anymore. And, you know, there's so many problems here and so much stuff to work on. For me, it's really hard to imagine that there is a one ring, you know, IR that basically fits all of these problems together. You know, another huge issue that I think that we just have to kind of recognize and is not independent of this discussion is the fact that, you know, if we're preparing as an academic, one of my responsibilities is to help prepare, you know, our students for a lifetime of innovation in this space. And we need the broadest participation possible, because this is where the future is. We need as many people as possible to be able to engage in these sets of problems. And we need to broaden the workforce that is working on these computer engineering problems. And I think that IRs actually play an important role there, because they are a natural point of interaction and interoperability between lots of things. I'll talk a little bit more about some experiences there. You know, and I think really, you know, because we don't know what the right model is for doing this kind of really hardware software space and navigating that, what we need lots of innovation, but that innovation needs to be served by a marketplace of ideas. And that marketplace is going to then need some way for these transactions to happen. And I think that while much of the discussion about IRs is around, and you know, we can think of it as an intermediate representation, sometimes people talk about that. They also really mean an internal representation. How do I internally represent these types of operations in my system? But there's another part of what an IR can be, which is, you know, a place for interchange, a place for interoperation. You know, I can mean something different there. And IRs are a huge opportunity for us to be thinking about how do we build not just a tool chain, but like a marketplace of tool chains that basically work cooperatively with one another to you know, allow more innovation in this space. I think critically that innovation has to come with you know, that marketplace will always have some cost of entry, because complexity is part of the cost of entry, and managing complexity is part of that cost of entry. But you know, the reality of this in the hardware space today is that cost of entry actually comes in dollars in addition to complexity, and it's incredibly high. and that many times there's not a lot of incentive to sort of make it easier for people to bring in new ideas and new tools to this marketplace. But I think there's a real opportunity for open source to change that, and we've already seen some great things along that line. So I just wanted to kind of highlight just a couple of different questions that we've been looking at that, I think this question of interoperability is more than just an engineering question of how do we link these things up. There's a lot of really interesting, hard, and exciting research problems that interoperability begs to, asks, and that we need good answers to. So, one of the designs that really just kind of blew my mind about what is possible with regards to interoperability is this work by my colleague Jonathan Balkind, on bring your own core, and the idea that you could build a system where you could swap in and out different types of cores, OpenSpark, Ariane cores, all kinds of different stuff, and it just all clicks together and works. Like that's as an architect, that kind of, I was like, okay, I understand in theory that might work, but like actually building something that does work and actually does allow you to like Lego piece these things in, it really opened my eyes to like, oh yeah, we could actually build much more interoperable systems than what the current tools are doing. And here, interoperability means, sitting in the cache coherence protocol for this whole system, and, working between those. So like there's a lot of opportunity for new interfaces that enable this type of stuff. Another thing that, another interesting research question that I'm personally super interested in is how do we democratize hardware and accelerator design? I think that, and how do we support the innovation? How do we support innovation and new ways to think about these types of problems? So I think the last talk was a great example of some really innovative, approaches to this, where we can model things as procs, and then things procs link up together, and they were able to build this whole tool chain. I would love for lots of things like that to happen that don't require teams of, large teams of Google engineering teams to go after them, but, a grad student, a pair of undergrads should be able to kind of ask and answer those types of questions, because I think that's how it works in the software space. And I don't see why there's really any reason we can't do this in the hardware space, as long as we give the basic building blocks that they need in order to do that. So one of the areas that we've been working on is Pertle, as was mentioned, which is a Python-based approach to hardware design. It's an elaboration through execution model, which is similar to Chisel. They were sort of built around the same time in parallel with each other. And it allows you to build out lots of things very quickly, and then because it's software, you can build abstractions on top of that. So for example, if you want to have one of the abstractions that's built on top of Pertle but not built into Pertle, is the notion of these channels and processes that push and pull things between channels, which I think is, it's like maybe 6 or 7 screenfuls of code to be able to do that. Because you can take that idea of a channel pushing in something and pulling from it, and then write software that abstracts it, and then now you have software which you can build on top of that abstraction. And one of the things that I really put as a metric of success is I do this work with our early research scholars program, which takes second-year undergraduates and brings them into research. And it's an amazing program here at UC Santa Barbara. And getting second-year students designing real hardware. The second-year students basically built a little, matrix multiply accelerator unit that did some neural network stuff, and in hardware. That was pretty exciting for me, and sort of like a good measure of, yeah, we're actually moving the bar on, who these design questions are accessible to. Another class of things is like, okay, there's this lowest level abstraction about how do we, write about hardware at this lowest level, at this gate level, but then there's, okay, we can talk about the architecture at the core level, and how do we build cores where we can plug these things together. But, increasingly, as we start scaling up and out, rethinking the whole way that we build servers and what it is that the software is serving there, I think is really an important question. And so Jonathan has done a lot of great work on open source hardware platforms for being able to ask and answer these types of server level questions, which I think really is only possible through interoperability. And then the final thing I just want to mention at super high level, the types of research that we love and that we at UCSB and that we're, the IRs have to be a really critical part is understanding new technologies. And so, for example, we have a big project on superconducting logic and temporal based computation. And that was only possible because we had these IRs to be able to build on and around. Not to say that we need to then extend our IR to be able to do these types of computation, but that easy interoperability, gives you the Lego blocks of hardware design that you can then build up and out from very quickly. So for me, one of the things that I think when I think about what do we need from an IR, I think that there's always going to be IRs in terms of intermediate or internal representation, but I think also we need to be really thinking about what it means to have an interchange representation. How do we share hardware designs with one another in ways that are going to be useful to the types of tooling that maybe need to interoperate? I think here, we can draw inspiration from, again, some of the work that happens at the software level. I think protocol buffers from Google are a great example of that, but there are many other technologies that sort of look like this, which basically give you a way to say, like, here's a schema. This is what this is, and here's how you share it, and this is what all these pieces mean. But don't get into the whole, okay, and here's the transform over it. Here's how you walk it. Here's how here's the rules, the algebra that describes the transformations that are safe to do. It just gives you the set of, the primitive alphabet that you need in order to actually start these things communicating. And I think in the hardware space, that's actually pretty missing at the moment. Oftentimes these tools will take something down and we'll bring it to, to Verilog or System Verilog, and then we'll share the System Verilog. But System Verilog is not an interchange format. System Verilog has a lot of problems if you think about it in that way. I think a part of that is really that less can be more. In fact, I would argue less is absolutely more in this space in particular. The kitchen sink approach to, while a kitchen sink approach may make sense in some contexts, I think as an interchange format, the real value of it is in saying what is not in there. And because the more of those things that you add in, the more of the cases that you need to be able to reason about. And those cases can be super complicated. I mean, having built some commercial tools for, that ingest Verilog and System Verilog, man, there are some scary basements in there about what does this statement mean in this context, and what is the hardware that gets generated from this, and that the answers to those questions in the scary basement are oftentimes, it is tool dependent. You have to know someone in the company who builds that tool to be able to ask them. And if you don't happen to have someone an employee from that company handy, meaning sitting next to you in your, at your large company, you may not be able to get an answer to that other than through test and experiment. So I think as an interchange format, as any sort of representation, that's not okay. We need to have a much clearer defined set of semantics that say, this is what hardware is, and this is how we share it with one another. And this is not just a hypothetical scary basement problem. Like, a lot of the stuff that we really want to build in real hardware is ill-defined. So, System Verilog, for example, if you just talk about memories and block memories, yes, you can specify arrays, and yes, you can talk about things you can do to the arrays. And yes, I think actually Verilog is pretty well defined about what that means. But when you actually take that and then synthesize it, and you talk about a specific block memory, that's where these tools all break down. And you need to have an understanding of the library you're targeting, and how do I write that code in Verilog in this way so that my tool can infer the right thing. There should be no need to infer anything if I think we've done our job well in finding a good interchange representation. the question then is like, what is that Goldilocks set? What is the set of things that we actually need? And we don't want more than that, but at the same time, we can't have less than that, because then you can't take on the problems that people actually care about. So I think who's been successful in doing what I'm talking about in terms of interchange formats or shared formats here? I mean, I think there are a lot of examples from the hardware software community in sort of the hardware design architecture space. But I think there's another one that I want to kind of just point out that I think is really useful for us to think about, which is SMT. So these SMT solvers, they're all based on this incredibly complex but incredibly powerful sets of formal reasoning tools that all link together, and different theories sort of coexist in the same space. But they have made just amazing strides over the last decades. Really innovative stuff happening that's just like transforms our understanding of things that you can prove about a system. And how did they do it? I think in my personal opinion, I think part of it is that they really got behind the idea that we as a field, they as a field, I should say, are gonna have a shared format that they basically say, yes, this is how we write SMT problems. And, it's not super pretty to read, but like they have a well-defined format. And every year, they basically run an SMT shootout where they basically say, here's the set of challenge problems for us as a field. And here's the, we all agree, this is how we read what that problem means. And we all, and then you have to actually come up with, find the answers. And that sort of shared, not tied to any company, not tied to any, specific tool chain type of approach, I think has been really powerful. And I think some of the things that were mentioned in the last talk about, like, there's reticence of building on other people's IRs when those things are intermediate representations is absolutely true. I'm not a huge company, I'm a professor, and I feel that because those things move quickly. But an interchange representation, interchange format, I think is something that we could still all agree on and we could still kind of get behind if we built some interesting challenge problems for it. So at a super high level, there's been lots of great work on IRs already. I mean, I'm going to shout out LLHD and Fertile, of course, which have done awesome stuff. And look, there's sort of an easy problem of hardware IRs, which in the last talk was there's sort of data flow representation. We can all translate between these basic operations super easily. I think the much more interesting thing is memories, because when you start talking about multi-cycle memories and multi-ported memories and how many ports does this thing have, how do I generate this type of block RAM versus that type, and what types of memories do I actually need? I think that's a really important and interesting question. And I'm glad to see I saw that on the panel discussion for later. But two other things I want to mention. One, composability. One of the things that really is always shocking to me is, like, if you have two pieces of hardware, each of which is well-defined with well-defined inputs and outputs, and then you link them together, that may not be well-defined hardware, because you may have introduced loops into your design by the way that the inputs and outputs link up to each other. And so that's a weird problem, right? I mean, that sort of says how early we are in thinking about composability in a hardware sense. That we don't have a well-defined notion of functions that we can say, oh yeah, that I can abstract this away. You can't actually abstract away just the data flow, graph, and use that as a module. That is not they're not the same thing. So we need some cool, we've done some work on wire sorts to try to figure out, a language for talking about these problems and detecting these issues. But I think there's a lot more work there, especially as you start talking about sort of richer interfaces where you want to have, ready valid style or queue style, or, some of these questions that were coming up about sort of interrupt type things, or feedback and pipelines. Like we need terminology for talking about these things precisely, and being able to build a family of interconnect protocols which are well defined, which let us be able to actually compose and link hardware in reasonable ways. So I think this is a super interesting problem. I'm glad to see that there was a lot of good work already happening in space. And I'm sure you'll hear more about it later. So what's the view from Santa Barbara? That's the view from Santa Barbara. But we need to really, just high level, we need to broaden participation. And I think any of these questions about what we do in terms of IR, we need to have that as part of our thinking there. How do we get more people involved in what it means to build the future of computers? We need new hardware capabilities that basically, and those hardware capabilities require a marketplace of innovation. And we need that marketplace to have low entry fee. And I really believe that we can work towards common hardware interchange formats that are going to make it so that we can actually do the innovation that's needed, so we can figure out how to actually build systems in this very new way. Thank you.
Thank you for a great talk. So who has some question? So what do you think about the question? One question, but I'm not so sure you're familiar. Chips Alliance, recently they are working on interchangeable FPGA format. And they use sort of like what you are saying. It's not that they want to do that as an internal protocol for the tool. There's a cap and proto, it's an alternative to protobuf. And they are doing that for interchain FPGA. So, but it's out after TMAP. So what you are asking for our community to do is also equivalent, but before TMAP. so
yeah, I mean, I think it's really interesting. Like, I think there's a lot of innovation that can be done at the FPGA level. I mean, we talk to people working there. I mean, they have all kinds of really cool tools for being able to like more closely manage your placement and get in there and deal with the guts of the design in cool in interesting ways. But like, then we force everything. When I see when people build research that like tries to link these together, we push everything through this weird channel of Verilog or system Verilog, where like it was never built. I mean, those languages were never built for doing hardware design at all in the first place, let alone being designed as a language to interchange hardware in this way. So I think, yeah, if we really want to unlock that ability, I'm glad to hear that that's work that's happening, because yeah, I think there's a lot of opportunity if we can really unlock the opportunity in the devices and expose that in reasonable ways to a set of tools that and hardware and software abstractions that can be built on top of that. Yeah, that's cool.
any question?
Question in chat.
Yeah.
Okay.
Theory of why marketplace forks haven't created more of the interoperability to date. Yeah, it's a good question. I mean, I think when you're talking about marketplaces, you're talking about incentives, and what is the incentive for a large company? I won't pick on any company in particular, but like if a company is makes money through selling a particular type of hardware or particular types of tools that support that hardware, like they're not necessarily interested in upsetting the status quo on that, right? And I think that there are now examples of this where open source tools. I mean, I think RISC-V is an amazing example of that, of something that was open that really was disrupted. So I think the reason the marketplace is in need of disruption, I think is the answer to that question. And open source is can be a great force of disruption in a positive way. I will say also that I think that you need a big enough, for that to happen though, you need a big enough community of people, and I think that that for a long time, like there was not a big enough community of people who really cared about sort of doing innovative things in the hardware space, like a huge community. And now, like, people realize, no, we have to do this. we have no choice but to do this. And there's a much broader community who's interested in this, and that's a huge opportunity to really build some community around that. And that I think that is part of how that how that marketplace forces are shifted.
Have we seen that from anybody other than Xilinx, any of the major EDA companies?
Seen what? I'm sorry.
Seen this interest in collaboration in a shared manner, and with the broader community, like these interchange formats you've been talking about. Or is it really just a university small teams at companies kind of thing?
Yeah, I think that's a fair question. I think that sort of what is the barrier to entry, is an important question, right? And so if the people who are entering, if the only people who are spinning chips are like, there's only 4 companies in the world who spin chips and no one else does, then there's not a lot of push for you to do anything that's going to support a broader set of things, because you're going to spend your money supporting the 4 companies who are bringing you money. I think that as we, in this new era, more and more people are going to have reasons to want to spin chips, but I think also more and more people are going to want to be able to navigate this space between FPGAs and more configurable hardware. We're going to have to be able to understand how to do this, whether or not we spin chips. And so, yeah, I think in the past it has absolutely been an area that has been dominated by a few large players.
Yep, I agree.
So let's tag the speaker, and then we are going to move to the panel. Idea is that Sheng is going to be chairing the panel, but he has some questions, and hopefully we can open also to the people in the audience to ask questions. We'll see how he will in charge of it. So he decides how to manage. But he has a set of questions, and we can all start there. So you have it, Sheng.
Oh, okay. So
a little introduction for Sheng. Sheng is the student. Uses Santa Cruz, so he's working on LiveXD. Now he's on Xilinx for this quarter, so he's working at Xilinx with a compiler floater.
So hello. So let me introduce our panelists first. The first is our Scott Biner. He is a professor in UC Santa Cruz, and he's previously working on the Verticality compiler building. And the second speaker is the Mark Heffernan, so from Google XLS team. And the third panelist is the Cruz Lattner from SiFive. He is leading on the circuit project. And fourth is my advisor, Jose Renau. And the last one is the team Sherwood from UC Santa Barbara. So all these members has a great experience on designing the hardware IR. So my first question would be, so there should be many optimization regarding the performance in your IR design, such as the cache locality or to reduce the branch prediction rate. So what have you done, and what's some other consideration points that you have been considered of? So maybe we start from Professor Scott Beamer.
Hello, yes. I'll add one small clarification to my bio. I'm not a Fertile compiler creator. I'm a Fertile compiler user.
Okay.
Actually, I believe we have one of the creators on this call. They can maybe introduce themselves and be promoted panelists that they would like. But in terms of this question, I'm a little confused about how this makes. Is this for a software IR or for hardware IR? Usually in a hardware IR, we're talking about like gates or components, and so the notions of caching and branches, it seems very much like attached to a CPU ISA. So I'm a little confused.
It's more like how. I guess there's not a clear boundary between what you so-called hardware and software IR. I guess that they are now. You could think it as a software IR if it's much more familiar.
Well, I think that's true for HLS approaches, but I don't think that's true for, I see HLS as a particular programming abstraction that is one way to produce hardware, but at the hardware level, you're dealing with cyclic graphs and you're dealing with implicitly parallel constructs, and like the notion of time is quite different, things like that. And so I don't think that branches and loads and stores in HLS and things like that are really the same thing as the hardware layer. And I think that one of the challenges is in the space of IRs is making sure that you separate the concerns there clearly and make sure that you don't have a one size fits all kind of answer to this big problem that we have with hardware design.
Mm-hmm.
Okay, so the way I took the question, it was more that we load very large net lists, very large designs. So if we are not careful with the cache locality of those designs that we load, the performance is going to be very low. So that is more a scalability issue. That if we do like a small hello world, doesn't matter. But if you do a very large design, just a graph, as Chris Lattner was saying, so you start to traverse the graph, suddenly your cache miss rate goes to nowhere, and you don't scale.
Oh, okay. So you're talking about making the tools themselves scalable.
Yes, I think that's the way I saw the question.
Yeah.
So in our case, we have trying to reduce the pointer size. We, for example, try not to use pointers, so we use relative pointers to a memory location, which improves performance, but it really complicates our life. So sometimes it's one of those things like, yes, great we did. Oh, I hate that we did it. So it's not a clear cut answer for me.
Yeah, so from the circuit side of things, I think that, and I'm sorry, I didn't have a chance to prepare a talk to introduce circuit and the philosophy and things like that. I think you can cross-reference Tim's talk, and it's basically everything Tim said is the motivation for circuit, in short. But the way we're looking at it is structurally, if you look at the generation of hardware, it's very similar to the compilation of these massively huge software code bases with a few specific differences. And so one of the funny things about software compilers is that the software compiler ecosystem has delegated all the parallelism, scalability, other things like that out to the build system. And so it has never entered into the world of dealing with the fact that our builds are massively parallel, multi-core, distributed across multiple machines and things like this. And so from my perspective, I think that distributed systems aren't a novel innovation anymore. and yes, we need to squeeze pointers and we need to like make things fit in memory, but really the caching, the distribution, the parallelism are all the big pieces. And once you solve the scalability problem, then you can work on the constant factors as well. And as we're looking at designs with billions and billions of gates, and we want to get turnaround times to be more interactive, I think we have to look at this from a different perspective. And fitting on one machine just doesn't. It's an inherent bottleneck for scalability.
So, any comment or answers from the other panelists?
Yeah, I can add a little bit. On the XLS side, we haven't yet gotten to the point of these kinds of optimizations. Typically it's some new input tickles some performance bug in our stack. Some super linear or something or other in some analysis or transformation, and kind of hammer them, deal with those in an ad hoc basis. And the size of our inputs aren't that big yet. One thing, we're not representing net lists. We're representing higher level operations, which then get emitted as Verilog, and so that certainly cuts down on the size of our graphs by at least an order of magnitude. But certainly once we get to that point, there's a lot that can be done in shaving node size down, and reducing levels of indirection and things like that. And I think there are some natural seams for parallelization as well. For things if they across threads, or potentially if it's a very large design across machines as well. But that's certainly something to consider. In previous compilers I've worked on, it's like we live in this nice little world of everything being local, and at some point everything just kind of falls apart, and we have to enter this realm of parallelization and lower level optimizations to keep things scalable. But there's always this trade-off between these performance optimizations and complexity. Sorry, kind of like Jose said, where you're making things more complicated and harder to deal with because you need them to be faster.
Okay, thank you. So let's move to the next question. So in each of our hardware IR, so there are many types for each of the nodes. So, but some node types are infrequently being used. So how do you think this kind of nodes? It's unnecessary, but adding these kind of nodes might hurt your performance or your scalability. So it's kind of question like, were you adding a new node type freely without constraint like a CISC in CPU, computer architecture domain, or a risk philosophy in computer architecture? So that's my question.
I can start if you like. I'd say there's no fixed rule on this. It's always a judgment call. Fundamentally, all you need is an AND and a register, but that'd be a terrible compiler and hard to reason about. There's this trade-off between adding more ops, having potentially capturing some higher level semantics, which may help you in the analysis, may help you even generate a higher QOR end result, as opposed to decomposing it into its more primitive operations. But then on the other side, every new op, there's this kind of multiplicative complexity that you're adding to your system, to your compiler, that every new op, basically every single pass needs to know about it, and what's called like the expression problem or something like that, and are related to it. And so you have to you can't just add everything. Your compiler quickly becomes very hard, or passes become very hard to reason about. Even with canonicalization and things like that, to try to limited the forms of your IRs, it still is hard. And so like I said, we don't have any rules. It's always a judgment call. Is this going to capture some useful semantics? Is this something that we actually want to emit in the end and keep it preserved all the way through? Those are things which inform the decision. But it's always weighing the cost and benefits, where the cost is really that multiplicative complexity.
Yeah, I totally agree with Mark. And just as a reference for my students, the student approach, many times they have a new functionality, they like to add new gates just because it simplifies their specific problem. And the rule that I have is, you have to convince me. You cannot add a gate until you convince me that we really need a new gate, because then it really complicates the life for other passes, other students, just to get the things up and running. So I try to put the bar very high to add a new block gate.
So that's, yes, but so I'm particularly interested in the answer from Chris, because I see the MLIR try to create many dialects in the whole flow. So how do you handle this kind of complexity?
Yeah, so I think that I would give the completely opposite answer for a fairly meta reason. So Circuit's a structurally different project than something like Fertile or LLHD or XLS or something like that. And so what Circuit does, and again, I apologize for not giving an intro talk, I think that would have been much more helpful, is that Circuit tries to pull together the hardware design industry into one framework. And so, in fact, we have a full implementation of the Fertile IR in Circuit that we at SiFive are using. We have an implementation of LLHD I don't think it's fully complete there, but it's largely there. And we have a general abstraction layer that's kind of like LLVM-ish, right, for that mid-level, Verilog level representation of a design, for example. But what is interesting and different about this is that it's not trying to force all these very different worlds into one thing. If you look at even LLHD versus Fertile versus XLS, for example, the type systems are all quite different, right? And so Fertile has very complicated type width inference logic that happens within the compiler. And so you want to be able to model that correctly based on the Fertile semantics. And you don't want to like fudge it and try to make a one size fits all solution for this. And so what Circuit does, and this is building on top of MLIR, is it allows you to directly model each of these worlds and then allow them to interoperate with each other. And so one of the things that Circuit provides is a very nice abstraction on top of Verilog, which then carves the problem into, first there's modules, and there's the basic things that hold the universe, modules and instances, basic and parameterized Verilog and all that kind of stuff that like holds the world together. On top of that, you then have the combinational logic, so your AND gates and muxes and stuff like that. And then next to that, you have the sequential world, right? And the sequential world, as everybody knows, is really complicated. And so it separates these out as different things that then compose together. And the composition of that, I think, is the key thing. And what that allows you to do is, if you're building, for example, a fertile compiler, is you can choose which of these pieces are useful to you and then put them together. Now, the interesting thing that MLIR brings is that you can mix these worlds together. What MLIR calls each of these worlds is a dialect. And so these dialects can be mixed. And so, of course, we have designs that have combinational logic, they have sequential elements, they have modules. They also have like if-def nodes and all the other weird things you need to generate like beautiful Verilog coming out of the tool and things like that. And so being able to compose these things together leads to a fundamentally different design for the compiler, because the compiler is then designed to be open. And what that means, the open world assumption for compiler IRs means that the way you design the compiler is pretty different in some simple ways, but that makes it way cheaper to add a node. And so in an MLIR-based compiler, generally what you see is there's a much higher acceptance of nodes. And generally what you want to do is you introduce nodes when there's a high-level concept that you can express and you want to lower out of. And so what you think about is a pipeline of lowering and progressive lowering. And you think about the transformations you want to enable at each level of abstraction. And then the cost of the node itself isn't super high. It's how does it fit in this system, right? And so the dynamics are quite different in that sense. And so it also means that if you're coming from HLS, then sure, you should have a lot of very HLS specific things. And Circuit provides, for example, John Dem on the call is building all this elastic interconnect stuff that's very related to like latency and sensitive communication things, right? And that's very different than muxes, right? And so being able to model that in the system and being able to progressively lower out of that is very helpful, and being able to model those abstractions where they are, I think, is pretty useful. So it's very different because it's a very different kind of a thing in a sense. And so I think that all the points that were made by others are really true when you're looking at one specific thing, right? And so, if you have an AND gate and a exclusive OR, do you have an invert? Do you have a bitwise not? Well, it could just be exclusive OR with -1, right? And so when you're designing a specific part of this space, you want to think very carefully about the IR design trade-offs of that, because your pattern matches and stuff like this have to deal with all the permutations and things like that. And so there are those inherent problems that come with an IR. And so Circuit has similar answers within the combinational dialect, for example, of like, you want to be very careful about what trade-offs you make. But on the macro, it's the opposite answer.
Mm-hmm.
I have a follow-up question there. Then, I mean, one of the things that I find an interesting trade-off point is, okay, if I have this thing I want to be able to do, or this concept I want to be able to express, how quickly do I get into some sort of tool that's going to then work on that for me, or I'll build that modification in that tool, versus doing that at the language level, like, building software abstractions on top of that. I think back to Haskell as an example, right? Where they're like, we will not allow mutability in this. And that forced them to really innovate at the language level about how they're going to build new types of abstractions on top of that.
Right.
And so that's something that I kind of, I feel that tension oftentimes in our work. Like, yes, we want to kind of move into a tool because we're the people who build the tools, and I understand that. But at the same time, what I really want to be able to do is enable a much broader set of people to build totally new abstractions by writing software that they understand, that doesn't necessarily build on.
Well, and what do you mean by software? Do you mean like standard programming, not Verilog, like a normal programming language?
Yeah, not Verilog, definitely not Verilog. Yeah.
To me, I find it really exciting and interesting and inspiring, this rise of these generator frameworks, right? And so you see Chisel on the one hand, but also Magma, and there's many of these frameworks that are coming up that are generator frameworks, also HLS and other tools and technologies as well. But one of the things that I like about the generator frameworks is it's saying that there's two worlds. There's the world of the IR. It's the graph. It's, you know, and you can pick your IR depending on what part of the space you're interested in, right? Whether you're staging you know, you're assembling an SOC, and so it's an IP exact level of abstraction or something like that, or if it's at gate level, or, you know, there's lots of different places in between. But then there's the imperative world of the code that you run, right? And so that means that the code that you're executing, the Python code or the Scala code or whatever, ends up being the user interface. And so that partitioning between a user interface layer and the graph layer that the compiler works on is, I think, really important, because imperative programming languages are more expressive, right? It's effectively the metaprogramming layer. IRs are easier to transform. They're declarative, right? And reason about and analyze and do, you know, detect bugs and whatever it is, formal methods, like all the compiler sorts of things are easier there. And so bringing those together, I think, is really powerful. And it's functionally what you see on the machine learning world side of things as well, right? Where you have your Python API like Keras using imperative Python code to stage a graph. And so this pattern is, I think, a very useful pattern when it comes to systems building. And it leads to both good usability, if you design it right, for normal people, but then allows compiler nerds to come out and play and do cool things on the tool side of things too.
I've run into some of these challenges at a practical level, and so I'm happy to hear suggestions from the committee on this. So as somebody who's using Fertile from application, sometimes for our transformations, we are not just lowering, we're raising. We're looking at Fertile nodes and taking hundreds of thousands of them and putting them together into a new super node of some sort. And so this is the challenge we have, is that we can easily add IR nodes within our code base, yes, but that has its own caveats to it, right? Because now we have an IR node that, sure, our code base knows about it, but then if we ever want to use another Fertile path later on in that execution, it's not going to know what it is. It's going to barf, right? And so it's been this challenge of how to handle this. Fertile gives us this escape hatch of these annotations where you kind of, you know, bury some metadata in the IR node that's not really typed. That doesn't really quite handle it for our cases. This is some kind of continual friction point for us, where for application, we really want to have these higher level new IR nodes. So currently our code base does introduce new IR nodes, because we spent so much time to compute what they are. They actually, these new super nodes that have, you know, the equivalent of 1,000 or 10,000 Fertile nodes. We don't want to lose those after finding them. But yeah, now we've done this, we can't run the same Fertile process anymore. So it's a challenge. I'm happy to hear more suggestions from the audience on this.
Well, so Fertile, the concrete design of Fertile itself has a number of challenges, including the type system. For example, you can't represent an AXI bus. You can, you know, there's like a variety of things that are challenging with that. At SiFive, we use Chisel and Fertile for roughly all of our products, which is great, and it's been very good for us in terms of the tooling ecosystem, things like this. But we've also realized that we need to move beyond, and so we're looking and building a replacement for Chisel. And one of the key design points of that is taking this concept of, you know, a generator roughly is a function from the name of the generator, the ports coming in and out, and the attributes attached to it, and then it produces the graph, right? And so that's what a generator roughly is, right? And so that is really interesting, because each node in the graph is itself the signature for a generator. So a node in a graph, it has inputs, outputs, it has a label, and it has a bunch of attributes associated with it, right? And so what this staging from, I have imperative code that puts out a graph, doesn't have to go all the way from the user's code to gates, right? It can just lower one level of abstraction, right? And so you can run the generator for your SOC, and it can put out the level of abstraction that here are all the IPs that are connected with buses and things like that. And then you say, okay, well, this IP is itself a generator. I can run this abstraction, you know, run this again, lower it to the next level of abstraction, and expose the top level blocks, and then keep going. The interesting thing about this is coming back to declarative versus imperative, and the benefit of this is that now you're lowering all these levels of abstraction within the IR itself. This then allows you to build the tooling and do the analysis and do, for example, verification at the right level of abstraction. And so one of the big challenges that I see in the hardware space is, of course, verification problem. Verilog is a huge issue here, right? Where on the one hand, if you're designing a high abstraction system, you're thinking about counters and state machines and other other things we talk about, but you can't express that in Verilog. And so if you're going to go do verification, the first thing you have to do is raise the abstraction level of the Verilog back up to, this is actually a state machine. I need to go poke it with my, my logic, right? And there's no inherent reason for losing that information from the generator framework other than the way they were designed, because they, just like Keras with TensorFlow, right? It lowers all the way down to matrix multiplications, even though Keras internally has layers, for example, as an abstraction, right? And so not capturing that in the IR isn't inherent. It's just kind of the design point of the tools today. So I think that there's a lot of opportunity to kind of capture that and do the progressive lowering within the system, then allowing you to, you as a, you know, if you're a hardware designer and not a compiler systems person, you can then, you know, you accidentally become a compiler engineer, you're implementing a lowering, but you feel like you're just implementing a generator like you would in a normal system.
In our case, when a student wants to annotate a group of nodes to have some functionality, they have usually two approaches. One is either they can create annotations to the nodes. It's like, say, these belong to group ID 3 or whatever annotation they want to create. The other one that is also quite powerful is that you can get and create a subgraph. So you can get a group of nodes, create a subgraph, and then if you traverse the original graph, that node is just a call to another graph. So you can, the option traverse down, up and down. So there are several iterators to traverse up and down the graphs. But it's a way to, if I have all those nodes and they have some common functionality, then you can create a subgraph. And maybe you find this thing in many places, you call that subgraph from many places. So those are the two ways that we do to avoid the creation of extra new nodes. It's either you convert to a subgraph or you attach annotations. Attaching annotation is always tricky because if you do a copy propagation pass or whatever, it might lose the annotations. While creating a subgraph, you have more control. But that's, we have a couple of nodes that didn't allow to be deleted.
And one trick you can also do is you can have black box nodes. So for example, you say I have a external module in your IR, and then you put a bunch of annotations on that. And on the one hand, you don't have the problem with optimizations going and changing it. And so you don't get constant propagation and things like that going through it. And then you can get it to the right place, and then you can expand it out where you want to. And you can do things like that. That's another good trick.
Okay, so very good discussion on this question. So let's move out to the next question. So as we, memory usually has many configurations, and each of the memory compiler might generate different layouts. So how do you manage this kind of generality? And what if some X memory compiler breaks your assumption on your IR? So what's your strategy to solve it? So okay, let me call Jose. Do you have any comment on this question?
So I don't have any good answer. The thing I have seen is to punch out the module and then just sort of expose it, and then someone has to type by hand to fix whatever you want. But really there is not an easy answer for this. At least I don't know. If someone has an easy answer, I'd like to know.
Yeah, we don't have an easy answer as well. We haven't gotten too deeply into memories, but certainly initially we're kind of treated as an externality. You know, again, I guess going back to like the abstraction level that we're targeting, you know, not the highest level of HLS, but maybe, you know, dialed a couple notches down, where the designer would, you know, pick the particular aspects of the memory, and that just becomes an input to our system. And then, you know, they can iterate on that and try, well, what if I make the memory a little bigger or smaller? But it would be an external or change properties about it. But it'll be an external thing that then feeds into XLS. You know, perhaps down the road that will change. You know, but at the moment we're not. That's where we're dealing with it.
Yeah, I also think that this is kind of an inherently hard problem because memories are both, they're very diverse, and also people care a lot about them. What we've seen that works well on the fertile side of things is that there's a variety of outlining options and things like this. There's a bunch of annotations that can pull into that. We have a memory compiler wrapper thingy that then handles that in a little bit of an abstract way. What I'm interested in us getting to is getting to a mode where, on the one hand, we do have standard things that are out of the box, solve the normal cases for most people. And so if you're using something that's fairly standard, you have a good thing to reach for. But then also, if you want to reach down to the PDK and use an exact node that you want, go for it, right? And this is one of the advantages of a generator, is that in a generator, you can say, hey, if I'm going to TSMC7, boop, and go to that exact PDK node, or that like hand optimized RAM. And you can then tie the models and things like that into it. I mean, to me, I draw inspiration from C in many ways. And I look at the reason C was successful as such an amazingly powerful abstraction language for CPUs was that, on the one hand, it provided a lot of the nuts and bolts that was fairly general and could be compiled in an efficient way to many different architectures. But on the other hand, it has inline assembly. And so, if you're trying to close timing on an aggressive latest generation product, then you got to do what you got to do. And so having the ability to reach all the way down and take full control of things, I think, is really important for getting the best quality results. Even though, of course, we as compiler people always want it to magically work, I think we also need to make concessions to when it doesn't work out for the user.
And that's a really interesting point about the inline assembly. And how do you make that interface actually work? And defining how those things link together.
Yeah, hopefully with fewer horrible register constraints and things.
That's volatile everywhere.
Expose reload to hardware designers.
I mean, one thing that I found I really a lot of good discussion here already. I mean, one thing that we found in Perl that was really helpful was thinking about ports as an abstraction, even more so than memories. And then those ports are then linked together with the fact that they actually share some common structure behind them where the things are stored. But I mean, I think just to kind of hit a pin in one of the things that's really tricky about this is like, because the semantics are different, but very similar, right? But they're not so similar that you can just swap one for the other. Like you have to push some of those design constraints back into your design. It changes the way that you have to write your hardware. And so, yeah, I would love to see, but at the same time, I think many of those changes you can wrap automatically, right? You can say like, okay, if you make it like this, we can generate for this and this, but we can't generate for this one. And so if you want to be able to do that, okay, now you need to do some work and make sure that these extra constraints are held, for example.
Well, I think it's also interesting to look at folks using traditional Verilog flows as well, because they have all the same tricks, right? And whether they're doing that wrapping and with if-defs in the Verilog source, or with Tickle by ripping nodes out in the back end or whatever, it's the same kind of a thing. And so I think that pulling those tricks into a more structured framework, I think, is really helpful, because it gives you the ability to have better tooling and stuff like that.
Yeah. So one thing that you touched on that I think is I'd be curious to hear from the group is, oftentimes I hear about sort of the downstream tools, right? And so someone way downstream is saying like, hey, we need to make a change to this design because this doesn't meet timing this way, or there's some other design constraint that's really complex that this way of doing things doesn't meet. And then being able to push that back up the design in some meaningful way. And I'm curious about whether people have kind of how they deal with that question or / problem.
We all want to hear the answer.
Stumper, yeah, okay, sorry.
So I guess that one way that we are trying to deal, but is that we're able to generate back. We all can generate Verilog, no? But we are working with other language besides Verilog. So that yes, we are trying to generate back the higher level languages that we have to. Now it's always ugly. It's like generating Verilog. It's always a problem how to do it. Personally, I don't like generating the Verilog. I think we should try to not debug on Verilog, and that will avoid many of our problems of generating beautiful Verilog and things like that. It's like, I would like to treat it more like JavaScript. So you might program in TypeScript, you might program in those things, or Reason ML. You have the JavaScript, but you don't have to touch it directly. but your VM runs JavaScript, doesn't write TypeScript. If we do this and they don't have to debug the JavaScript, I think it will be much better for our community. But the verification teams, they are used to, for not use the word obsessed, but they are used to work with Verilog. And if you start to spill bad Verilog, they don't like it.
Well, they generally don't have a choice.
No, but they have. It's like, if you think about it, they have two Verilogs. They have the Verilog, the programming types, and they have the netlist. When they debug timing, they have to debug the netlist, and that's unreadable. And so there are, but they want to keep working on the other one. So sometimes I think we should spill netlist. So it's totally unreadable for them. It's semantically correct, but unreadable. So you don't even try to debug that thing. The problem is that we are quite readable, but not enough. So they want to make it more readable. So sometimes I think it should be generating just ugly netlist so that they don't try to read it. And then we have a higher level abstraction to debug. But
yeah.
That's not.
Yeah, I mean, I think it's really interesting to me to see the tension here as well. I don't think there's any magic answer, but your original question was, you build a thing, you don't get the quality result you want. What do you do about it? I think that one of the major tensions there is the tension in the system design between magic and predictability. And I think that oftentimes in C compilers, but also in hardware, people want magic because we can use auto-parallelizing technologies to take imperative code and turn it into parallel code. We can do, like, there's a lot of stuff that exists in the world, but it ends up being very magical, and it leads to these performance cliffs when things work or things don't work. And so I think that there's a lot to be said for very predictable compilation flows where you give the user, again, I think C is a good inspiration here, right? With C, a C programmer has a pretty good mental model of what the performance of the code they're writing is if they're writing low-level C. But then they can build abstractions on top of it with templates or other things like that if they'd like to. On the other hand, if you take extremely high-level languages like JavaScript and things like that, you don't really have the same performance model in your head, and you can get really good quality results with JavaScript or other high abstraction languages. But it's just that when things go wrong, they go really wrong, and there's not much you can do about it. And so I think that that's one of the inherent tensions that we face in systems design and in the how we express our designs.
So since we are talking about a Verilog readability, so Jack actually has a question. So usually we want to produce a readable Verilog output from our compiler, but to keep a readable semantic, we have to leverage the high-level struct along our compiler stack so that we are possible to produce a readable Verilog. So how do you? But this also introduce extra difficulty for our compiler passes. So how do you handle these two contradict need from readability and the compilation lowering problem?
Yeah, it's a I think fundamentally hard problem of having an optimizing compiler, generating something that's readable. We do our best to try to keep preserve names and things like that, but fundamentally the optimizing compiler is kind of scrambling things up, and so it's really hard to have something readable, certainly at the compared to a human written code. In XLS where there is some structure, certainly structure which is preserved from the higher level. Like I mentioned, these procs and things which may exist down at Verilog level. So there's some kind of structure from the which mirrors the source code. But within any of these these clouds of combinational logic, crazy things can happen, and you end up with a bit of a mess. It's a little hard. One thing that's kind of interesting in the HLS space, at least tools which are taking some higher level description and then emitting Verilog, and then the Verilog goes to a synthesis tool, is that we don't have to go all the way down to the lowest level. I mean, we can try to preserve some structure, not do maximum level of optimization, because we know that
we have the synthesis tool backstop to actually maybe really scramble things up when it generates the net list. But then again, we also want to have some kind of if we're going to say doing automatic pipelining, something like that, where we're taking the design and then breaking it up into pieces. We want to have at least an accurate representation of the timing. So we'll need to do some optimization, but there is some kind of tension there. What do we leave for the synthesis tool? Helps if we leave more for the synthesis tool, it helps Verilog readability. But then again, the models that we're dealing with as far as timing and things like that are not as precise. So yeah, it's hard. People want Verilog that a DV engineer is used to looking at human written Verilog. Verilog's a terrible thing, but written by a human, it may be manageable. But then machine generated Verilog can be a terrible beast. Yeah, no easy answers. We have some heuristics, but that's about it.
Yeah, in our case, we try our best to do something reasonable, but it's clearly not the same as you will type. But what I was mentioning is as a research site, I keep thinking that why do they want the Verilog? Usually it's because they run Verdi and they have those tools and they are used. But if we were able to have like those tools, but working with more the chisel of the language you use, so that you don't have that problem, I think it will really simplify many of those things. And that's why I was mentioning the TypeScript kind of approach. So they debug directly TypeScript, they don't debug JavaScript when they are having those tools. They could debug JavaScript, but they don't do that because it will be much harder for them. So if we were fixing the tools, I think that is the verification, because the timing they have to do netlist, so they already have something unreadable. So if they were having the Verdi equivalent, then we might be able to skip this problem. In the way that, why don't we generate a readable assembly? We can do much more readable assembly, but now no one cares. In the past, before there were GDB, they would have cared, because how do I debug this thing? But we're still not there.
Yeah, I mean, I agree, and I agree with both. It's an inherently hard problem. I think that there are two ingredients that I think are worth keeping in mind. One is that location tracking is the bread and butter basic thing that you need to enable the tooling ecosystem that Jose is talking about. And so location tracking itself is pretty hard in a compiler, and you need to kind of design for that up front and make sure that every optimization that you add in is thinking about that, because if you don't do that, it's very easy to end up with scrambled output that then, it's just it's not the inherent part of the problem that you're struggling with, it's the accidental part of the problem. I think the other thing that I've seen being a challenge with Chisel, for example, is that Chisel was designed with instantiation as the model, and it wasn't designed with this idea of generating, for example, parameterized Verilog. And so the output you see is, unlike what a human would generate, because it doesn't have the abstractions in Verilog that Verilog can express. And so this itself is not the inherent parts of what Mark and Jose were talking about, which I agree with completely, but they're kind of just design artifacts of how Chisel was built. And so as we look to bring parameterization into the generated code and things like this, we can lead to much more natural looking meta structure, at least for the design. The module structure can be more controllable in what a human would look like, even though the logic within it ends up getting scrambled in certain cases. So these are hard problems, so I don't see a magic bullet for this.
Okay, so maybe we move to next question and we decide if we continue the panel or make the next speaker speak. I'm the next speaker, but I'm okay to keep the panel. So let's move to the next question. So how do you handle the global optimization? Because theoretically in your design hierarchy, you have many design instances. Do you copy each of the instance and the global optimization propagate to each of the instance, or you have a pseudo unified one and just optimize it in your IR? So maybe Jose, do you want to go first?
Okay, so the thing that we do is mostly we optimize locally per module first, and then we do a first parse there. Now, in the global optimization, we have tried a few things. but we have a global traversal. So the modules, it looks like a virtual flat. So we don't flatten the modules, but you traverse and you think it's flat. So that is being flattened. The issue is when we do annotations, so when you change nodes, so then we create the thing we were having, but we just remove it because it was not performed very well, is that you have another flat graph that it has annotations over the non-flat virtual hierarchy. So that then you have many graphs because you have the original, but now it looks like a virtual flat. And then we create a new flat graph with only the changes. You have done changes. You don't do changes, you don't keep it. Now, the issue with this was that when we traverse, now you have to keep checking in both sides. Do I have the original virtual flat or do I have a modified? And then I'll keep traversing the graph in one way or the other. So it was slowing down the performance in both cases. So we are trying to look for a alternative, a little higher performance, but it was working, that approach. That's what we were doing.
I can speak a little bit what we do in XLS, which is pretty simple. We just flatten everything, and then you get a specialized copy of everything. You know, at the moment we're not haven't run into scaling issues. Like I said, we're not generating a net list as well, which helps. You know, as far as the size of the graphs that we're generating. You know, anything that's not flattened, you know, it would be, you want, you know, explicit reuse in your hardware, you know, you would represent it as a proc, which is, you know, which is then maybe used from a couple or communicates with a couple of the instances that it that use it. But yeah, a flattening is our approach.
I'd also say that Chisel and Fertile have a hybrid approach where most things are flattened at generation time, but Fertile has a pretty rich way of doing instance hierarchy specific annotations and things like this, which are extremely useful. And so you can have you know, a 4-core complex and then put annotations on one of the cores and things like this and keep a unified representation of the tiles. In practice, it seems like we get a lot of instantiation of each of the tiles anyways, and so it's kind of a hybrid, mostly flattened thing with some amount of deduplication kind of going on. One of the things we're investing in now at SiFive is getting an explicit Chisel API so that you can put in instances and refer to them multiple times, which we just absolutely need for the scale of, you know, the many core designs that we're doing. And that's a pretty big deal. The challenge though is that whenever you get into not flattening, you do lose optimization opportunities, right? And so I don't think that it's really a question of like, do you flatten or do you not? The question is at what point in your compilation pipeline do you flatten, right? And so I typically look at the difference between, you know, the human written normal Verilog that somebody would write is usually not flattened, and usually use parameterization and you use, you know, the plus operator or whatever, things like that. And then when you get down to a net list, then you flatten. And so there's good reasons for scalability on this, and the specialization benefits you get from instantiating, I think, are important, but doing that late in the pipeline, I think, is really valuable. And I think that it's for build times and memory use and scalability of the tools and things like that, as well as the fact that if your generated Verilog is flattened, then your verification engineers feel like they want to get toggle coverage on all the things, which is also a challenge and maybe not as helpful as it would otherwise be. So we're looking to, you know, we're currently in a mode where we largely flatten things with some exceptions. We're going to a mode where flattening is not the default, and we're going into full-on parameterized IR because we need to get to much more scalable designs.
We've come across this as, you know, people working downstream on Fertile trying to optimize Fertile for making simulators. And yeah, we've had the same issue where initially we flatten things, do all sorts of optimizations to it. Over the summer, I had a master's student do some really great work looking into how do we take advantage of, you know, Fertile's dedupe capabilities to do dedupe in their simulators. The issue we now have is once they're having a shared instance, some optimizations may not apply to all instances, right? That's the challenge we ran into right away, was that even though it's the same module instantiated in multiple contexts, those contexts actually change the effective constraints on it. And so summarizations may or may not be allowed in that case. So you kind of are dealing with that. So our best solution so far is simply figuring out what's the most strict, you know, superset of constraints, and then having that global instance be satisfying all of those. But perhaps, you know, with more time, we would figure out it's better to actually have 2 versions of our module to have, you know, for constraints A versus constraints B. Yeah, this is definitely an important, interesting question.
Yeah, I mean, it's also really relevant and related to that discussion we're having about lowering versus raising, right? As if you're coming from a unified representation, then of course you can instantiate it out. But if you're coming from an instantiated representation and trying to dedupe, you have to kind of raise it. You have to kind of pattern match it back up. And this is where you can get accidental things. We use a tool called Firesim, which is in the Fertile ecosystem as well. And Firesim has a bunch of really cool optimizations where you take slices of the design and you run them in series, even though they're instantiated out in a real ASIC, you actually share gates in the FPGA to run this. And it's also a related thing, right? Where you're trying to pattern match in these duplicated chunks of the hardware and maintaining the fact from the original design side that it was unified and then not throwing it away before the tools get a chance to do their thing seems like a better approach. That's the direction we're going.
I'll just throw out there that this exact same problem exists in your physical design flow. I mean, it's the difference between a hierarchical, synthesis in place and route versus not. And in that case, performance problems in the tool can turn into correctness problems if it takes you 2 weeks to, turn your Verilog into a GDS. So anyway, just noting the same problem applies at every level.
Okay, so Jose, what do we do next? So it's the panel time is theoretically, we are already 11:45. So should we continue the panel?
So let's do this way. There is anything that any of the panelists or the audience wants to bring a question?
I do have several questions at hand, 5 to 6, but you decide. You're my boss.
No, but I'm saying if someone has some question,
Okay.
and then otherwise we can go to the speaker. But if there is anyone on the audience or on the panel who wants to query the other part of the panel.
Okay, someone asked a question.
Hey, hi there. Yeah, so long-time listener, first-time caller. Very, very high level. How far, so this might not be directly on topic, but just I'm sure you guys have learned opinions on this. How far are we from something like Keras or PyTorch specification for a neural net to instantiation of, like a 2 approximation in terms of optimality on an FPGA or an ASIC, where the person that writes the PyTorch model doesn't have to know anything about compilers, let alone synthesis. So if that's not clear, I can say
so
a little bit
you're saying when does it become possible, or do you say when will it be optimal? Because if you're asking if it's when is it optimal, the answer is probably never.
Well, that's why I said 2 epsilon approximation or whatever the kind of jargon is here. So I'm asking. So
if I put my take on this, so it really depends what you are targeting. Like if you are in a big company, let's say Intel, and you are able to squeeze like a 5%, it's worth to put a lot of effort. And the reason is because you have such a high volume of 5% over so many pieces makes a lot of sense. And with 10% reduction in area will make a multi-million, maybe more cost benefit. So it's a very different targets. They have a very different optimization willingness to go there. But many of the players, when you are in the ASIC, they have extremely high volumes, so they are willing to put a lot of effort to improve. Now you are an FPGA or lower volume ASICs, then it's a different topic.
Yeah, so I'm imagining some kind of futuristic sci-fi scenario where your average data scientist at let's narrow the scope a little bit of the question to companies that are not like Google scale, Facebook scale, where they run models and serve trillions of customers over, I don't know, a year's span, but like, so low volume designs, but still interested in performance. So that's what I'm imagining. In fact, I'm a PhD student that collaborates with like physicists, scientists, experimentalists, and they want to deploy at, for example, edge detectors, some kind of in silicon neural networks or compression schemes, et cetera, and they want the easiest time designing those quote unquote hardware algorithms that they can get. And so I'm wondering, like, hence my question, right?
Okay, so you're not asking how do I literally run MobileNet or something on an FPGA. You're saying how do you get to that abstraction level, or?
Well, I'm asking, how do I get MobileNet spec that you can get from PyTorch Hub right now, or from wherever it's stored? How do I get from that specification of the architecture of the neural network down to something that does run on an FPGA? How far are we from that compilation pipeline or path or whatever being easy enough to use for your average experimental physicist?
Yeah, I mean, I think that Xilinx and other FPGA vendors are providing some of these tools today. One of the other interesting things that's happening in FPGA architectures is that they're moving away from just being Cs of LUTs and BRAMs to getting dedicated hard blocks that have accelerators in them. And so here you're touching into the whole kind of mess of AI software compilers. And that itself is a very complicated, dangerous, and twisting space right now. I think that my best guess on that, if you're looking for a time frame, is 5 or 10 years for it to be really great. But today we're seeing pieces that are possible. Mike Erbach on the call gave a talk where he took the MLIR machine learning stuff and composed it with the HLS stuff in Circuit and showed end-to-end flows where you could take a neural network and compile it down to an FPGA. But I would say these are research prototypes at this point. They're not necessarily the production thing that you'd want to use.
That sounds actually right up. So was that during this symposium that this talk was?
No, I would, if you send me an email or send Mike an email, I can connect you to. He gave it at MLSys or some other conference.
Oh, sorry. This is Mike from Alloy. Mike, I forget but he's associated with Alloy. I think some company.
He's actually on the call. So.
Oh.
So, yeah.
Yeah.
And I'm happy to connect you if you want to.
Sure. Yeah, sure. Thanks.
But if you're looking for productions stuff, I think that's kind of the union of all the problems of designing for hardware, all the problems of machine learning accelerator compilers, and like pulling these things together into one stack and working out all the integration layers at the many levels of abstraction you're dealing with, which I love because it's a really interesting and hard problem. But I think realistically, we're still a number of years away before it's truly great.
Yeah, that's why I narrowed down to like smaller volume than your typical commercial effort would need to get return on investment. So like, a couple of runs a year, or I don't know, something like that. Anyway, thank you.
Okay, so actually I'm the next speaker, but now it's 11:53. So is it okay that everyone stay 10 more minutes? Maybe I could speed up my speaking and okay. Okay, let's start wasting time. Hi, so I'm Sheng-Hong Wang. So today I'm talking our LabHD update, a multi-threaded fast hardware compiler for HDLS. And today, actually in our group, we will have two groups. And Sakshi, she will talk about the challenge and principle to design a new hardware discrete language using the existing compiler framework in the open source domain. So let's start from my talk. So research problems. So there are many new hardware discrete languages, but this new high-level semantic already gives extra burden on the compiler. So for large SOC design compilation, it already takes minutes to hours. So not even to mention that the traditional simulation, synthesis, place and routing stages, which usually takes hours to days. So we LabHD want to solve this HDL compilation first, then extend to the later VLSI domain. So what we have been done is we build a fast compilation infrastructure. We have our two IR, LNest and LGraph. And we have multi-language support for Verilog, Fertile, and Pyro. And now we are focusing on how do we parallelize the LabHD framework. So here is our framework nowadays. So now we could support the highest level Fruto, the Fruto team call it Turtle. And we leverage the Chisel 3 compiler to generate the Turtle protobuf format. And then we interfacing this protobuf into our high-level IR nests, and then doing some SSA transformation and loading to our graph representation, doing most of the compilation passes there. So the speed is good. So it's around 33 faster than the original Scala proto compiler in a single threaded. But we are looking more opportunity to how could we get it even faster. So here I'm trying to talk about the parallelized programming 101 regarding to the LiveHD. So for compiler passes, two modules can considered independent if they don't need to communicate information to each other. So usually people call it embarrassingly parallelized. And but if the two modules are dependent regarding to a compiler passes, then they must be processed in a specific way, either in a top-down or a bottom-up way. So what are the special challenges in HDLS compilation parallelized? So the first challenge is we need to understand the dependency relation between the whole design hierarchy so that we could extract the parallelism from the design dependency graph. Let's step back and see how does non-hardware language generally handle this problem. So for C or C++ language, they have this include syntax. So a top module like the source code I put here could easily know, okay, these foo and bar are my child function, and the C++ compiler will have a pre-processed phase to handle this included syntax. Then the C++ compiler could know the design dependency. But HDLS generally don't have this kind of privileges. Verilog has the include syntax, but the included module doesn't need to have a dependency with this current Verilog source module. So it is basically useless. And for other HDLs, their import syntax tends to be implicit and scalably distributed in the source code. So this is the challenge we need to solve. And LiveHD builds and understand the dependency by building the dependency tree at the same time that our IR construction phase. So once we get the design dependency, we could understanding, for example, take the right-hand side design hierarchy as an example. The M1, M2, M3 is the leaf node in our dependency tree. And LiveHD could apply a bottom-up parallelism if these modules has a dependent relation regarding the past, and we could extract parallelism from this tree. And we call this bottom-up. We're starting from the leaf, and for example, this M0 is the parent module, and he has to wait all the children being processed, then he could continue join the thread pool processing. If the modules are fully dependent, then we could just compile them in any order as long as we have enough thread resource. So here is a simple flow chart to give you a test what the parallelism happen in the LiveHD. We have several passes. Some of the passes are fully parallels or embarrassing parallelized, but some of the passes have a dependency relation and need to follow the bottom up. So here, the leaf node has to be processed first, then the parent node could continue the job. So this slide shows the compiler passes that we implemented in LiveHD. I'm not going detail into this table. But I do want to talk a little bit more why some module has the dependence regarding to compiler passes. The main reason is mostly because of the I/O. For example, if you have a hierarchical graph and you want to connect your hierarchical graphs in a way, the connections need to know each other's I/O definition or the position. And the sum of the I/O has a tuple data structure or array data structure. It's not purely a scalar variable as we all see from the Verilog code. So we need to solve this I/O tuple data structure. And some I/O has the attributes that need to be propagated so that the whole compiler passes could leverage. For example, in LabHD, we analyze the fertile bit information starting from the I/O and propagate to the whole graph. So these are the main reasons that there are some dependency passes in LabHD, and we try to pursue as much fully parallelism path as possible. So here is one technique one methodology we proposed. So there is a LNAS to L graph IR transformation inside LabHD. If you want to compile the top module and submodule parallelly, the top module, because the top module needs to connect to the submodule. So if they are compiled parallelly, the submodule's I/O information might not be ready at that time. So that creates the dependency problem. So in LabHD and in these passes, we introduce a unified I/O. This is a pseudo I/O that every graph has. So for the top module point of view, he could think, okay, I'm going to connect to this submodule. And this submodule must has a unified input and output. So this is a known information. So the top module could directly connect to this unified I/O. And this unified I/O is actually a tuple data structure that could be resolved in the later passes. So in this way, we turn the LNAS to L graph translation from a dependency problem into independent modules. That's the first methodology we proposed. And second, we want to make our compilation flow really fast. So even though some of the passes could be fully parallelized, but we try to merge them with some other bottom-up parallelized passes, so that these compiler passes could be integrated into one, and they could just traverse the graph just once, because the graph traversal is regarded as an expensive operation. So we're doing this merged trick so we could boost our compilation throughput. So let's take a look about some brief evaluation. So we have created 1.3 million lines of code combinational circuit. And this circuit has around 3,300 modules. The average size for each of the module is around 400 lines of code. And the whole design dependency tree is balanced with an average 4 children. So we benchmark these 1.3 million size circuits with the original Fertile compiler and our LabHD compiler. But notice that we're starting from the turtle format, not from the chisel source code. But as we can see, the original Fertile compiler will take around 2,000 seconds. For our LabHD single-threaded, it takes around 1 minute. And for 8-threaded, it takes around 70 seconds, which is 114 times speed up. So though this is fast, but we do discover some scalability issue for our high-threaded approach. So good, we uncover another research problem, and we are currently looking into it. But as I said, we starting from the turtle format, but the actual bottleneck, we actually has another bottleneck. So this graph is Chisel end-to-end compilation time for that 1 million circuit size. So for the front-end Chisel code to the turtle format in either Virtual or protocol buffer, the time spending from the front-end is around 1,800 seconds, which nearly taken 50 times of the original compilation flow. So for our flow, we could achieve fast compilation, but the front end is a problem for us. So we hope the future Chisel compiler version could partially solve this problem, or we could, yeah. So the next target. So far we have some specific memory configuration supported, but we try to make the memory support to be a generic, so that we could compile a more real circuit from the Boon, from the Chisel source code. And we want to improve the scalability from the multi-threaded live HD compilation. So that's my presentation today. And I'm going to switch to our next speaker, Sakshi. So Sakshi, do you want to share the screen?
Okay. Thank you, Sheng, and hello, everyone. So I am I'm Sakshi from UC Santa Cruz, and now I'll be taking over to make live HD an easily verifiable flow. For this, I'll be sharing with you a guide for rapid creation of new HDLs. So, we know that digital hardware designing is getting easier due to shifting from using the age-old Verilog to new HDLs, which compose of practices like object-oriented programming and agile designing. But we see a problem. With every new HDL being created, there is a corresponding compiler flow for the language. There is no unified workflow, and every language creator is spending a substantial amount of time for creating a compiler infrastructure for the language and validating the end-to-end flow. This means duplicated efforts. So can we avoid this redundancy and save engineering effort? Can we have a shorter development cycle and thus provide reliability and trust earlier in the design flow? So thinking about that problem, we have an idea. If we leverage a pre-existing multi-language compiler flow for our new HDL, we will have a compiler flow ready to use for general reference purposes. Let's call the pre-existing compiler flow as YFlow, and the newly developed language as Xlang. So this will have a ready to use. But what about the reliability of the flow? Do we have a good coverage? How do we test it? Isn't it error-prone process? Doesn't look like a simple idea after all. Well, let's have a way to verify the Xlang compiler flow by having high coverage. Let's not implement reference compilers, and let's leverage YFlow cost effectively. And unlike traditional methods, let's avoid the time-consuming simulations needed to verify the designs. So according to our proposed guidelines, to accomplish the new compiler flow by leveraging a pre-existing compiler, we need to implement 3 passes: Xlang input interfacing, Xlang generation, and semantically same program generation. And this would help in establishing the 3 testing procedures as per our guidelines. That is Xlang to Xlang leg, Xlang to Verilog test, and random or synthetic program generation. So we use these 3 testing procedures to build our own Xlang compiler flow. Here we implemented a new HDL pyro and leveraged the pre-existing compiler LiveHD. So we implement the passes proposed to build the end-to-end compiler flow and further build trust in the system using the 3 testing procedures. Let's see what these procedures are. Coming to the first procedure, that is Xlang to Xlang led, we start with the Xlang input interfacing and use yflow to generate the Verilog v1. Further Xlang generation is used to get the Verilog v2. v1 and v2 are checked for logical equivalence. A large subset of Xlang can be tested using this process, but it might not cover all the features of the language. Let's take a very simple example. Let's say yflow doesn't understand -2 and it converts it to 2 every time. The leg would still pass this case. So then how do we deal with this problem and ensure a better coverage? For that, we propose the second testing procedure, that is Xlang to Verilog test. Here we start by generating semantically same code in the Xlang as well as Verilog and process it through this flow to check logical equivalence. Sorry. This process detects the remaining subset of bugs in the entire Xlang compiler flow developed. To get a reliable system with maximum coverage, we need to generate a bank of randomly as well as synthetically generated code to test through the first and second testing procedures just discussed. Well, there are some constraints on the proposed methodology. To start, the new language should support the complete set of yflow internal representation. For example, yflow may support negative edge flops while the original designers did not want to support them. If the new HDL would support the complete set of yflow IR, this would enable the interfacing of multiple HDLs with each other through the yflow. So nevertheless, if some features cannot be supported, in such cases, Verilog tests that trigger those features in the yflow IR cannot be used. So by following our guidelines, new HDL developers can leverage existing multi-language compiler flows for rapid generation of the new HDL. It enables having a reliable design flow without implementing reference compilers. Along with detecting any errors in the Xlang compiler flow, we could convert Xlang to any other language generated by the yflow. So thanks for everyone for their support and contribution to the work, and thank you.
Thank you, Sakshi. Thank you, Sheng, for the talk, and thank you, everybody, for staying up to the end. So this is the end of our section, and hope that you enjoy. And we'll post Stephanie will post the video once she has finished processing. There is any question or any comment anyone want to share? You can send me an email, or you can mention it now. No? Okay, so thank you, everybody. See you around.
Thank you.
Bye, everyone.
Bye.